The equilibrium constant, which has the symbol capital K little c, is essentially a measure of where the position of equilibrium lies for a reaction at equilibrium, and it's in the form of a ratio. So to write the expression, it is simply the sum of the concentration of the products. So remember, square brackets stands for concentration, over the sum of the concentration of the reactants, and each is raised to the power of the coefficients in the equation. So what do I mean by that? Let's have a look at a real example. Reaction between hydrogen gas and iodine to make hydrogen iodide is a reversible reaction. So to write the expression for Kc for this reaction, we would write Kc equals, well, the products are the hydrogen iodide. So it's Hi. We always include state symbols within our square brackets. And because 2 moles of hydrogen iodide are formed in this reaction, we raise this to the power of 2. If it was 3, we would raise it to the power of 3, and so on. The bottom half of our ratio is the concentration of the reactant. So we've got hydrogen, and there's just one of those, so no coefficient, and iodine. Remember, state symbols in everywhere. So that is the expression for the equilibrium constant for this particular reaction, and obviously it refers to the equation as written. The concentrations of our reactants and products at equilibrium have to be determined experimentally, and if we were asked to calculate a value for Kc, then this is information that would be given to us. So having gone to all this trouble of figuring out a value for Kc for this ratio of concentrations of products over reactants, what does it actually tell us about this reversible reaction? Well, if Kc is greater than 1, that must mean that the concentration of the products is greater than the concentration of the reactants, because we're dividing a bigger number by a smaller number. That tells me that the position of equilibrium lies to the right. So, for example, in this particular reaction between hydrogen and iodine at 730 Kelvin, Kc is 46.7. There are no units in this particular example, and I'll go on to explain about units in a minute. So that means that, to all intents and purposes, our reaction has gone to completion. The position of equilibrium lies so strongly to the right that there's virtually no hydrogen or iodine in our equilibrium mixture. Conversely, if Kc is less than 1, then that must mean that the concentration of reactants, the bottom number, is bigger than the concentration of the products, the top number. So, position of equilibrium must lie to the left. If we have a look at another example, the reaction between nitrogen and oxygen to make nitrogen oxide, we can write an expression for Kc while we're practicing this. So NO, state symbol, that's the bit that lots of people miss out, raised to the power of 2, because in my balanced stoichiometric equation I produce 2 moles of NO, divided by N2 gas multiplied by O2 gas. And Kc for this reaction at 298 K is 4.6 times 10 to the minus 31. Again, in this particular example, there are no units. So at 298 K. This is a very, very tiny number, which tells me the position of equilibrium lies so far to the left that, to all intents and purposes, the reaction doesn't go at all. There is pretty much no nitrogen oxide in my equilibrium mixture. The nitrogen oxygen remain completely unreacted. So why do I keep quoting the temperature? Kc at 730 K, Kc at 298 K. Well, the position of equilibrium is dependent on the temperature. So Kc is dependent on the temperature. We know that increasing the temperature will shift position of equilibrium in the endothermic direction, and vice versa. So changing the equilibrium concentrations and therefore changing our ratio, changing our value of Kc. So although we don't need to know the temperature in order to do any equilibrium calculations, it's good practice to quote the temperature for which this equilibrium constant applies. The units for Kc must be worked out for every individual system. So the two examples I've already used had no units. Let's have a look at that reason. So Kc. To work out units, you just write out the expression for Kc, but only using the units. We're working in concentrations. So I had NO squared, so that's mole per decimeter cubed times mole per decimeter cubed. So that's the equivalent to the NO gas squared, which was the top half of my expression. The bottom half was the nitrogen and the oxygen. So again, mole per decimeter cubed for the concentration of nitrogen, multiplied by mole per decimeter cubed for the concentration of oxygen. And hopefully we can see that they just cancel out, which is why Kc has no units. However, this is not always the case. Let's have a look at the reaction between nitrogen and hydrogen, the Haber process. I'm sure we're all familiar. Making ammonia. Writing our expression for Kc, we have got product is ammonia raised to the power of 2, and on the reactants we've got nitrogen gas, no coefficient, and hydrogen gas, and we use up 3 moles of hydrogen, so we need to raise that to the power of 3. If we convert that into units, I've got 2 lots of moles per decimeter cubed at the top, and at the bottom nitrogen, mole per decimeter cubed, and I've got 3 lots of hydrogen, so that's going to be, bear with me, mole per decimeter cubed, mole per decimeter cubed. I'm doing this really long so that we can all be really sure we know what we're saying here. 3 lots of mole per decimeter cubed. Let's cancel out. So my units look to be 1, because the top layer is cancelled out, over mole per decimeter cubed times mole per decimeter cubed. Let's tidy this up. So that becomes mole squared dm to the minus 6. Now, even though it's multiplied, it's added because it's a power. So it's not 3 times 3, it's not to the minus 9, it's minus 3, minus 3, so minus 6. Now we need to bring it up over the line because we don't ever see units that are 1 over. So to finish, it becomes, almost finish, mole to the minus 2 dm to the 6. So note that we have changed the sign when we bring it up over the line. And then, if you are being absolutely correct, you put the positive before the negative. So the units technically are dm6 mole to the minus 2. But I've never seen an exam paper mark you down for not doing that last little bit. Okay, so let's have a look at a couple of exam questions. This is a popular one, the reaction between ethanoic acid and ethanol to make the ester and water. Write an expression for Kc for the reaction and comment on the units, and then use the concentration in the tables to calculate a value for Kc at 373 Kelvin. So, let's have a look at this. an expression for Kc. Well, our products are the ester, ethyl ethanoate and water, and our reactants are ethanoic acid and ethanol. I've only got one of each, so I don't need to worry about powers. I need to remember to put in my state symbols. Always write out the expression starting with Kc equals. Don't skip on that bit. So the ester, CH3, CO2, C2H5, and it's a liquid. Square brackets for concentration. Water as a liquid. Okay, and our reactants were ethanol, C2H5OH as a liquid, and ethanoic acid. So products over reactants. And we should be able to see straight away that there are not going to be any units because I have the same number of moles on the top and the bottom, and that's exactly what you would state in your answer to this question. Okay, moving on to part B. Calculate a value for Kc at 373 Kelvin. So all I need to do is plug the numbers into the expression, and I just need to make sure I plug the right number in the right place. So this should be quite straightforward. Kc is going to equal 0.981 times 0.981 divided by 7.033 multiplied by 0.0342. And when you plug that into your calculator, it comes out at 4.00. We've already seen there are no units, and a number greater than 1 tells us that the position of equilibrium lies fairly strongly to the right in this particular example. Moving on to my second example exam question. Phosphorus pentachloride heated in a sealed tube, and then give us the volume. So that should be piquing our interest. And equilibrium is reached. We've calculated a value for Kc, given that at equilibrium the tube contained. And we have got the number of moles of each of these substances at equilibrium. So let's start with our expression for Kc. It's going to be PCl3. Remember to put in state symbols. Cl2. And our PCl5 is our single reactant. Now, let's remember that square brackets denotes concentration of, and we haven't got a concentration, but we do have the moles and we do have the volume, and concentration equals number of moles divided by volume. So before I go any further, I need to calculate the concentration of each of these substances at equilibrium. So both of these, it's 0.04, number of moles divided by the volume. The volume is already in decimeters, and that one is 0.0042 divided by 2. Now I can work out a value for Kc. Kc is going to equal 0.02 multiplied by 0.02 divided by 0.0021, and that comes out to be 0.19. Now, I don't have the same number of moles of reactants as products, so I do need to work out the units. There are going to be units here. So on my top layer, I have got mole per decimeter cubed, mole per decimeter cubed, and on my bottom layer, I've also got, obviously, mole per decimeter cubed, which is one of them. Two of those cancelled, so the units are simply moles per decimeter cubed for this particular example. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.